Okay, geometry, we're going to move on into section 3.5 today. And this one isn't too bad of a section. It's a little bit interesting that your authors for this book chose to include this section right here within chapter 3, but I think there's an interesting reason why they do it, and I think it does make some sense. So what we're going to talk about today is covered in every single geometry book you will ever find, but not always in the chapter on parallel lines. Usually it's in the chapter on triangles, but today we're going to relate these two concepts right here with parallel lines and triangles together. So we're going to discuss postulate 3.2 today, called the parallel postulate. And I want to remind everybody that a postulate is a mathematical statement that we know to be true, but is so simple and so basic that it cannot be proven. So the parallel postulate says this: through any point not on a line, there is one and only line parallel to the given line. Okay, so as we try to digest that, let's take a look at the diagram down here on the bottom here. And what we have is just any old random line that I'm going to go ahead and call line L, just so we have something to name it, and then a point located somewhere other than line L. So this dot right here, I'm going to randomly call that point P. For point, get it? All right, and this postulate says now that there is one and only one. That's an important phrase in geometry right there. It means that something exists, but it exists uniquely and distinctly. We can draw a line that passes through point P that is parallel to line L. We can do it, but there's only one line that does that. So two important realizations right here. First of all, there are an infinite number of lines that pass through point P. I could draw one line looking here like this, and another line here, look, ooh, I missed, but okay, looking here like this, and another line here, and here, and here, and here. And basically, I could sit here all day and continue to draw lines in this pretty starburst pattern here that pass through point P. So there are an infinite number of lines that pass through point P. Furthermore, there are an infinite number of lines that we could draw that are parallel to line L. For example, I could draw one line here that's parallel to line L. I could draw another line here parallel to L, and one here, and one here, and one here, and one here, and I could sit here all day long and continue to draw lines that are parallel to L. There's an infinite number of those. So there's an infinite number of points that pass through P. I drew those in red a moment ago, and an infinite number of lines that are parallel to L. I have those in green here, but there is only one line, everybody, that does both of those things simultaneously. And so to do that, and to make this diagram look pretty here, I'm going to go ahead and clone that line here, which gives me something both congruent and parallel to it, and I'm going to move this new line up so that it passes through point P right about there. And what we have now, guys, I'm going to go ahead and call this new line, line M, is right now we have drawn the one and only line here that does the two things that we're talking about. This is the only line now that passes through point P and at the same time is parallel to line L. So this is one of the basic postulates of geometry, and as you look at it, it's one of those things that people tend to look at and go, oh yeah, obviously. Well, that's why it's a postulate and not a theorem. We can't prove it, but we can look at it, and with common sense we know that this is right. There is a line that passes through point P that is parallel to line L. And with that idea in mind, that certainly doesn't seem to have anything to do with triangles, but we're going to see in just a moment here with Theorem 311 how it is that that postulate relates to this concept. So everybody, if I can be honest with you guys, you are not going to remember everything that we're going to cover in here in the year in geometry next year, or 2 years, or 5 or 10 years down the line, but this might be one that if you're a parent and you have a kid then 20 or 30 years from now and they're taking geometry, that you might look at their homework to help them out and you might go, oh yeah, you know what? I kind of remember this basic idea. And this is called the triangle sum theorem. You're not going to remember that name, but you might very well remember what it says. This is one of the basic concepts of geometry. I should say the most fundamental and important concepts in geometry. The sum of the measures of the angles in any triangle, and I want to stress that word any. It doesn't matter what kind of triangle it is, whether it's acute or obtuse or right. It doesn't matter how big or how small it is. In any triangle, the sum of the measures of your angles is always going to be 180 degrees. And we don't use that word always all that often in mathematics, everybody, but that's exactly what's going on here. Now, this is a theorem and not a postulate because we can prove it. And again, we're not really doing a whole lot with formal two-column proofs in here this year, but let me just walk you through what's going on. So what you'll see here, guys, I wanted this to look good, so I went to GeoGebra and I drew a triangle, and each of the three angle measures I just randomly called A degrees and B degrees and C degrees. And now what we're going to do is we're going to take advantage of the parallel postulate that we talked about just a moment ago right here, postulate 3.2, and we're going to apply that postulate to this diagram right here. If you see, I labeled point P up there on the top of that triangle, and there is, according to the parallel postulate, one and only one line that passes through point P that is parallel to this line down here on the bottom, or I should say the line segment that I'm going to mark in red right here, guys, that makes up the bottom side of that triangle. So what I'm going to do is attempt to draw the one and only line passing through point P that's parallel to the bottom side of that triangle. And hopefully I did a decent enough job that you guys are going to buy what's going on here. All right, so using that postulate, we now have a blue line up on top that's parallel to the segment on the bottom. What in the world does that accomplish? Well, I think something that's kind of interesting. I'm going to take this line segment over here on the left-hand side of the triangle here, and I'm going to extend that line segment really just up into a ray. I guess I could make a line out of it if I wanted to, but there we go. And now, let me go ahead and take the bottom line segment in the triangle and let me extend that into a full line looking something like this. And what I want you guys now to notice is if we look at the two blue lines and the one green line, now I wonder if you're starting to see why or how this applies to what we've been talking about in Chapter 3. What we have here, everybody, are two parallel lines in blue cut by a transversal here in green. And now, all of those theorems that we learned back in section 3.2 about parallel lines being cut by a transversal, those theorems now apply to this particular setting because we do in fact have two parallel lines cut by a transversal. And one of those theorems that we talked about said that when that happens, if your two lines are parallel, which they are in this case, your corresponding angles are congruent. So if we take a look at this one angle in the original triangle that I had one tick mark on that was called A degrees, this angle right up here is a corresponding angle with that one, which means that this angle also has to have a measure of A degrees. Why? Because when you have parallel lines cut by a transversal, your corresponding angles must be congruent. Okay, now with that exact same idea in play, everybody, I'm going to switch colors here and I'm going to go to red, I guess, on this one here. And I'm now going to focus on this line segment here in the original triangle. Okay, I'm going to color that in red and I'm going to extend that one as well and make another line out of that. And now in this case, if we focus on the two blue lines and the one red line, let's ignore the green line for right now. Once again, we have two parallel lines being cut by a transversal. Okay? And once again, we can use the idea here that your corresponding angles have to be congruent. So this angle right down here, which we said was B degrees, would have to be congruent to this angle right over here. Those are corresponding angles between two parallel lines. And those corresponding angles must be congruent, which means that this angle would have to be B degrees. And we're almost there. The last thing we're going to focus on now is this angle in the original triangle right here, which had like a triple tick mark on it, and that one had a measure of C degrees. So now we're going to use a much simpler concept and realize that this angle here, C degrees, is formed by the intersection of the red line and the green line. And if we extended the green line up here and the red line over here, we have a vertical angle right here on top. And vertical angles, we know from theorem 2.1, everybody, with the vertical angles theorem, vertical angles must be congruent. So if this angle down here is c degrees, the measure of this angle up on top has to be c degrees as well. That has nothing to do with parallel lines, that just has to do with vertical angles. And now, everybody, now the really big important idea relates to the relationship here between these three angles up on top. As I think you guys know, the blue line that we drew up on the top of this figure passing through point P is, obviously, thank you, a line. And of course, all lines are straight. So that means that if we were to add together the measures of all three of those angles right there, they would have to equal 180 degrees. So my brilliant conclusion here is that, and any order you do this in is fine, B, which is right here, okay, plus C, which is right here, plus the A, right over here, has to equal 180 degrees. We see that up on the top of the figure, but let's not lose sight of the fact that A degrees, B degrees, and C degrees were actually the measures of the three angles in the original triangle. And if these three numbers, A, B, and C up on top add up to 180, these three together here, the A, B, and the C, they have to add up to 180 degrees as well. All right, so that's the big takeaway, and it probably would have looked better if we wrote that as A plus B plus C is equal to 180 degrees. But obviously, because of the commutative property of addition, nobody cares what order we add those in. So that is a long-winded mathematical way of establishing this fact here, that in any triangle, and I do stress the word any triangle, the sum of your three angle measures always has to equal 180 degrees. That is an irrefutable, unarguable law of mathematics, and it is always true. So you're going to see a lot of problems now moving forward that look something like this. And in fact, this concept right here is going to show up throughout the rest of the school year, you guys. It has a way of popping up in all sorts of different types of problems that we're going to be solving later on in the year, even when it's going to seem like we're well past this concept here. So what do we have, guys? We have ourselves a triangle, and two of the three angle measures have been given to us. We're supposed to come up with the third one. We're supposed to solve for x in this problem. So what are we going to do? We are going to use the triangle sum theorem that says the sum of the measures of the angles in any triangle is always 180 degrees. So we're going to add up our three angles. I always like to start with the variable. One of my angles is x degrees, another angle is 27 degrees, and a third angle is 79 degrees. And no matter what kind of triangle it is, no matter how big, how small, how wide, how skinny, how sharp, how dull, whatever, no matter what kind of triangle it is, that sum is very simply always going to equal 180 degrees. So the mathematician's way of doing this would be to combine like terms here on the left-hand side, and we would get x plus, let's see guys, that is 106 is going to equal 180. And of course then we would subtract that 106 from both sides, and those are going to cancel, and we're going to get x is equal to 74. Now, technically, you shouldn't put a degree sign after your answer there, all right? Technically, the x already had a degree sign on it, and we're just solving for the value of our variable here. So that, everybody, is our answer. X is equal to 74. If you were to include the degree sign right there, you're telling me that this angle is 74 degrees. And technically that's wrong, but that's not the kind of thing we're going to take off for at this level, so don't worry about that, but that's the correct answer. Okay? Now, if you are one of those people who doesn't like to nerd things up with an equation all the time, there is a way to do this, and I want to show you what I think is really the better way to do this as opposed to the way that most people do it, but this is just me. All right, what a lot of people do in these strictly numerical problems, guys, is they want to grab their calculator and they want to immediately put together the two angles that were given to them, which were 79 and 27. So they'll do 79 79 plus 27, and they'll hit enter and they'll get that 106. And then they will take the total, which is known, the 180, and subtract the 106 that they came up with, and voila, you get your answer of 74. That obviously works, but I'd really like for you guys to start doing this in a different way that is actually faster to do, and it's this. Start with the total, which you know is 180 degrees. And then from there, subtract the two angles that are known. So minus 79 and then minus 27 again. And now you guys, in one step, you can get that same answer of 74 as opposed to having to do it twice in a lot fewer keystrokes there. That's the way I would advise that you do that. Now, obviously, I didn't do it that way. Part of my job as your teacher is kind of to show you guys the quote-unquote proper way to do things, and you will notice that I, unlike some of you guys as I'm grading your homework and your quizzes and your tests, I like you to set up equations. I think that better illustrates a mathematical understanding of the concepts right here, but the real reason that I like to do a problem like this with an equation rather than simply to grab the calculator and get working is because that method of just using the calculator doesn't help you when you get to a harder problem like this. So why bother learning one way for numerical problems and then having to learn a second way that works when you've got variables involved? Why not just learn the one right way and do all of your problems the same way? So what's going on here, guys? Again, we have a triangle. The measures of all three angles have been given to us. But we got to be clear, angle A was given to us as a numerical constant, 27 degrees. Angle C was also given to us as a constant, 37 degrees, but angle B's measure is given to us as a variable expression. I don't care. I know what to do with it regardless. I know, because of the triangle sum theorem, I know that in any triangle, the sum of your three angle measures will always equal 180 degrees. So pick one angle and start with that. I generally prefer to start with the variable here, so that's going to be a 12x plus 20. There's the measure of angle B. And we're going to add to that the other two angle measures, which are going to be 27 and 37. And this theorem tells us that in any triangle, when you add up your three interior angle measures, you are always, always, always going to get a sum of 180 degrees. And now from here, it's not too bad, everybody. We do have like terms to combine on the left side. The 12x is just going to stay by itself. Oh, but let's see. The 27 and the 37 is going to get us 64. Add a 20 to that 64, and we're going to get an 84 there is equal to 180. We're going to subtract that 84, hither, thither, and yon. All right, those ones cancel out, and we're going to end up then with a 12x is equal to, I believe, a 96. And in our last step here, everybody, we're going to divide both sides by 12. Oh, and somebody was thinking when they made this problem, we end up with a nice, pretty answer of x equals 8. And again, that's all that we were asked to do. If I wanted to check this answer to make sure that it's right, here's what I would probably do. I would add together the measures of the three angles and make sure that it equals 180. So I've got a 27, a 37, and a 12x plus 20. Here's probably the most efficient way to do that. Let me clear that out. 27 plus 37 plus. Now the measure of the third angle was 12x plus 20. So I'm going to type in 12, but instead of an x, we believe that our x value is 8. So there's your 12x, and then a plus 20 at the end of all that. So when I hit enter, this should get me a total of 180 degrees, and sure enough it did. So I'm guaranteed now, guys, that I got this problem correct. All right, so the triangle sum theorem is really important. You're going to use it a ton during the course of the year. The good news is, everybody, it's not an overly difficult theorem to figure out. You just need to take your time and be patient with it and to try to set up equations rather than trying to do too much work in your calculator. Now, following up that theorem, we have another one here that's pretty important too. It's nowhere near as commonly used as theorem 311, which we just discussed, but anyway, let's take a look at this one right here. Theorem 312 is the triangle exterior angle theorem. I really wish that in contrast to this, they had gone back here and called this the triangle interior oh boy, I can't spell, interior angle sum theorem. That's what I would have really liked for them to call this, but that's kind of wordy right there. This would be, if I were in charge, would be the triangle interior angle sum theorem because it deals with adding up the measures of your three interior angles. This one though, guys, theorem 312, we're going to be dealing with an exterior angle in a triangle. So let's see what this says. We have a problem already in that I think everybody can understand what an interior angle in a triangle is, but an exterior angle is not something that we've talked about so far, so that can be just a little bit tricky. I'll show you what that means in just a second. But the theorem says the measure of an exterior angle in a triangle, and by a triangle, again, we really mean any triangle, is equal to the sum of the measures of the two remote interior angles. All right, let's see what's going on here. So it was not specific at all in this theorem what kind of triangle we are dealing with. And so for that reason, we can imply or infer then, everybody, that we could be dealing with any triangle in the world out there. So whatever it is you want to draw, great. I'm going to go ahead and draw a triangle that looks a little bit different than the one that we dealt with before. This is what we in the biz call an obtuse triangle because it contains one obtuse angle. I'm going to call that obtuse angle, angle 1, and the other two angles I'm going to call angle 2 and angle 3. Brilliant, Mr. Fontana. All right, now those three angles, 1, 2, and 3, are all located where? Inside the triangle. So those would be your three interior angles. What we're now going to do is create just one of the exterior angles in this triangle. And it's a really easy way, you guys, to create an exterior angle. All you're going to do is take one of the three sides of the triangle, any one you want. I'm going to focus on the bottom side, and we're going to extend that particular line segment in one direction only. We're going to make a ray out of that. So I'm going to take this bottom side here in the triangle, and instead of it ending right here at this point, I'm going to extend that bottom side over here to the right and make a ray out of that. And this new angle that was formed here, guys, is outside of the triangle, and I'm going to call that angle 4, and that right there is what we call an exterior angle in a triangle. Again, it is formed by simply extending one side of the triangle, and it's the angle between that extension and the original triangle itself right there. Okay? All right, so that's your exterior angle. There are more. Don't bother writing these down, but there's actually two at every vertex. If I had extended this side instead, angle 5 here would be an exterior angle, and then let's see. Here's angle 6, that's exterior. Angle 7 here is exterior. Angle 8 out here, and angle 9 right over here. Now, don't write this down either. Angle 10 is not an exterior angle. Why? Because angle 10 doesn't touch any of the blue sides of the original triangle. Likewise, angle 11 is not an exterior angle, and angle 12 is not an exterior angle. So, to be clear here, the interior angles are 1, 2, and 3. The exterior angles are 4 and 5, 6 and 7, 8 and 9. And then 10, 11, and 12 are just kind of extras. They don't really count at all. Now, I've made this diagram way too complicated, so let me get rid of all of this stuff and go back to just where I was with angle 4. Now that we have an exterior angle, we need to define one other phrase right here, remote interior angles. And in fact, this theorem even references there are two remote interior angles. So we better talk for just a second about what that word remote means. If I were to ask you guys what you think of when you hear the word remote, most of us would think about a remote control for our television. And a remote control, if we break that phrase down, is a device that allows you to control something from far away. So the word remote means far away. If you were to ever talk about a remote location, usually it's something that's out in the middle of nowhere and not near everything else. So, pretty clearly, there are three interior angles in this figure, angle 1, angle 2, and angle 3. But the two remote interiors are the ones that are far away from this exterior angle right over here. Now, probably the easiest way to think about this is, which of the three interior angles is adjacent to angle 4? Which one is closest to or next to angle 4? And that would be angle 3. So angle 3 is what we would call the adjacent interior angle. And there's only one of those. The adjacent interior angle is right here. That means that angle 1 and angle 2 are what we are going to call the two remote interior angles. Although you've got to be clear, it just depends on which exterior angle you're talking about. Remember, there were 6. But if we're dealing with angle 4, the two remote interior angles are angle 1 and angle 2. Those are the ones that are far away from angle 4. That's really where we're focused on. And now that we've defined what an exterior angle is, and we've defined what remote interior angles are, I think we can go about translating this theorem. The measure of an interior angle in a of an exterior angle in a triangle. So stop right there. Our exterior angle here is 4, so the measure of the exterior angle in a triangle. Got it. The next 3 words I read are really important. Is equal to. So obviously when I'm translating, that's where I put an equal sign. Is equal to. This next word is important, the sum. So that means that I'm adding 2 things together. And the sum of what? The sum of the measures of the 2 remote interior angles. And the 2 remote interior angles were angle 1 and angle 2. So the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. And that, everybody, let me go ahead and box that up. That is the triangle exterior angle theorem. Okay? The measure of angle 4 outside the triangle is equal to the sum of the 2 interior angles that are farthest away from it. Now, if you care why that's true, everybody, it basically relies on 2 facts. One of them is the interior angle theorem we just talked about. The measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 always has to equal 180 degrees. The other thing we know is that angle 3 and angle 4 right here form a linear pair. And that makes those 2 angles supplementary. So the measure of angle 3 plus the measure of angle 4 has to equal 180 as well. And if you take a look at what we're trying to prove equal here, let's take a look. The left side of this equation within the theorem is the measure of angle 4. I see that right here. So I'm going to isolate that by subtracting the measure of angle 3, which is a number, I just don't know what it is, from both sides of this equation. Those terms cancel, and we get the measure of angle 4 is equal to 180 minus the measure of angle 3. That's as much as we can do with that. Now, the right side of the equation in this theorem is the measure of angle 1 plus the measure of angle 2, which we see right here. So what's with it now? I'm going to subtract the measure of angle 3 from both sides of this first equation. Those cancel, and we now have the measure of angle 1 plus the measure of angle 2 is equal to 180 minus the measure of angle 3. So take a look at these 2 statements I have down on the bottom of my board here, guys. The first one says that the measure of angle 1 plus the measure of angle 2 is equal to this quantity right here, 180 minus the measure of angle 3. The second statement says that the measure of angle 4 is equal to, and oh, what a happy coincidence this is, 180 minus the measure of angle 3. So if we look at these 2 equations down here on the bottom, both of them on the right-hand side of their equations have the expression of 180 minus the measure of angle 3. And we really missed out on this concept this year, guys, because we decided not to cover much really at all of Chapter 2. But there's an important property in mathematics called the transitive property. And it basically reads this way, guys. If this expression right here, measure of angle 1 plus measure of angle 2, is equal to this expression, 180 minus the measure of angle 3. And then I follow this green arrow here. 180 minus the measure of angle 3 is also equal to this quantity right here. So it's kind of like we'd call this A, and it's equal to this B. But this is the same B over here, which is equal to this C. And the transitive property says that if A is equal to B, and if B is equal to C, you are then allowed to conclude that A and C have to be equal to each other. And that's how we can make the conclusion now, guys, that A, the measure of angle 1, plus the measure of angle 2, has to equal C, which is the measure of angle 4. And that's the theorem that we wrote down, although I think I did it backwards, but that's okay. Equations can be read in either direction. Okay, so those last couple minutes right there are not hugely important for you guys for understanding why this theorem is right, but we need to make sure that we've got this idea down here and we've got it written down clearly and that diagram going along with it. All right, an exterior angle's measure is equal to the sum of the measures of the two remote interior angles. Remote meaning far away. So let's do two quick examples with this one, guys, and then I think we're done for the day. All right, this is another one now that's pretty much just numerical, but I'd still rather set this one up with an equation rather than simply go into the calculator. So trying to translate the theorem, let's go back and let's read it again. The measure of an exterior angle in a triangle. Stop right there. We have a triangle here. You'll notice that line segment AB has been extended out to the right, and we could make a ray out of that. And we do have an exterior angle here, and that's going to be x. So the measure of our exterior angle in a triangle, what comes next, is equal to. So that's where we go ahead and put an equal sign. And what comes after is equal to? The sum of the measures of the two remote interior angles. So this angle right over here is the adjacent interior angle. But then this one and this one are far away from x. Those are the two remote interior angles. So we're going to take those two angle measures, add them together, and that's going to get us the measure of the exterior. This isn't an equation to solve, you guys. It's just an expression to be simplified here, and we're going to end up with x is equal to 104. And once again, since there's already a degree sign on the x right there, we're not being asked to find the measure of an angle. We're being asked to solve for the value of x. So we don't put a degree sign there, and x is just equal to 104. All right, not too shabby. And the last problem here is the same concept, but people find it a little bit more difficult because we can't just go to the calculator. What do we need to do instead? We need to read the theorem and we need to translate it word by word. This is a really important skill, and you guys dabbled in this a little bit in pre-algebra and algebra 1, where they gave you a verbal expression, you know, like 7 more than the sum of a number and 3. And you were supposed to translate that into a mathematical expression or an equation. Well, the same thing is happening here. So let me read that theorem again. The measure of an exterior angle in a triangle. So let's stop right here. The only exterior angle we have is this one right here. So that's what I'm going to begin with. 10x minus 14. Okay, the measure of an exterior angle in a triangle is equal to, so there's equals, the sum of the two remote interior angles. Now once more, this is the adjacent interior angle, which makes these two the remote interior angles. So that one is 71 and that one is 25. And this one is slightly more complicated than the one that we just did because the x is not already isolated. Let's see what we can do. Again, first I want to combine like terms on the right. So 10x minus 14 is going to equal 96. And then from here, everybody, we're going to add 14 on both sides. Those two cancel. And we're going to get 10x is equal to, that looks like 110. And lastly, we'll divide both sides by 10 here, and pretty as you please, we will end up with x is equal to 11. Now that should be our answer here, guys. If we really want to check it, that's not what I wanted to do. If we really want to check it, it's not a bad idea to plug that in and see what happens. So the 10 times 11 is going to get us 110. 110 minus 14, this is a 96-degree angle. If I were to ask you guys now to find the measure of this angle right here, probably the best thing to do is to recognize that we have a linear pair here and to take 180 minus that 96 that we just came up with. So let's try that. 180 minus 96 is going to get us, 84 degrees for the measure of this angle right here. How does that help us? Well, now we believe that we know the measures of all three interior angles in this triangle. So now we can add those three angles together and we should get a sum of 180 degrees. So we're at 84 plus 71 plus a 25. And sure enough, you guys, that got us a sum for our interior angles there of 180 degrees when we add all three of those together. And I feel pretty good then about that answer as we look at it. All right, guys, that is a wrap on section 3.5. So let's give that homework a try and let's see how we do with it. Good luck, and let me know if you guys have any questions. Go get them, everybody.